Hi everyone, my name is Prabhesh Shrestha and my student ID is 101538718, and in this video I'll walking you through to my assignment 3. This assignment covers two main topics: how 2D convolution kernels work on images and how a convolution neural network is trained on the CIFAR-10 dataset. So let's get started. We first have the part A, image convolution. So what is image convolution? Image convolution is a mathematical operation where slide a small matrix called kernel or filter over an input image. At each position, we multiply the kernel values by overlapping pixel values and sum them up to produce single output value. This is repeated for every position across the image to produce a new transformed image. We can see that here. So we are plotting the resulting image of the array. So convolution is the fundamental building block of a convolutional neural networks, and is also useful for classic image processing tasks like detecting edges, sharpening and blurring. And in here we can see that it is had been gray shaded. For question number A, I created a kernel to detect the 45 degree lines. A line goes from the bottom left to the top right of an image. The kernel I use is uh, this one. So the positive values too are aligned diagonally from bottom left to the top right, which means the kernel responds strongly when that diagonal pattern is found in the image. For question number B, I created a kernel to detect 135-degree lines that the opposite diagonal going from top left to the bottom right. So when we apply both kernels to the car image, the output highlights the diagonal edges that match the direction. So we can see that here. For question number 2, I applied 3 edges. The kernel one is diagonal corner detector. It responds to the areas where the top left and the bottom right are bright, while the other corners are dark, or like vice versa. So the corner 2 is Laplacian filter. It highlights region of the rapid intensity change in all four cardinal direction: up, down, left, right. We can see that here. And for the kernel 3 is a strong version of Laplacian with center weight of 8 instead of -4. It detects edges in all directions more aggressively, producing sharper but sometimes noisier image. We can see that here. And let's go to the data set. So we train our neural network on CIFAR-10 dataset. This is well-known benchmark dataset containing 60,000 color images, each 32 by 32 pixels, divided into 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep and truck. There are like 50,000 training images and 10,000 test images. Before training, we process the data by one hot encoding the labels, converting them to vectors of zeros and ones, converting pixel values to the float, and normalizing them to the 0 1 range. Let me briefly explain that each layer does. The Conpo V 2D layer scans the image with 32 different filters, each learning to detect a specific feature like horizontal edge, curves, or texture. The max pooling layer reduces the spatial size of the feature maps by keeping only the most activated value in each 2 by 2 block. This makes the model more efficient and reduce overfitting. The flattened layer converts 2D feature maps into flat 1D vectors so it can be flit into dense layer. The first dense layer converts the 2D feature maps into a flat 1D vector so it can be fed into the dense layer. The first dense layer acts as the classifier that combines all the extracted features to learn higher level patterns. And the final dense layer with softmax gives us 10 probabilities, one per class that sum to 1. The class with the highest probability is the model's prediction. So you can see that here. So for the it comes back as a overfitting. So when the train model of 50 epochs and plot accuracy curves, we can see that the training accuracy keeps rising throughout the training, eventually reaching 75 to 80%. However, the validation accuracy starts to plateau or even slightly decrease around epoch 2025. This growing gap between training and validation accuracy is classic sign of overfitting. It means the model is memorizing the training data rather than learning patterns that generalize to new unseen images. So I have answered this question. For question number 6, I have added an extra conv 2D layer for 64 filters 3 by 3 followed by another max pooling 2D layer. This gives the model two stages feature extraction instead of one. Comparing the two models, the bigger model with two combo 2D blocks achieves higher validation accuracy, typically around 70 to 75% compared to around 65 to 70% of the original. The extra layer allows the model to learn more complex, high level features, not just edges and textures, but parts of object and shapes. However, overfitting still occurs. The training accuracy continues to outpace validation accuracy. The deeper model has more parameters, which gives it greater capacity but more potential to overfit. For question number 8, I added a dropout layer with the rate of 0.5 between the flattened layer and the first dense layer. A dropout layer is a regularization technique that randomly sets 50% of the neurons to 0 during each training step. Think of it like this: every time the model trains a batch, it uses a randomly different version of itself with half the neurons disabled. Why does this help? Because the model can no longer rely on any single neuron being there. It has to build redundant, more robust representations of the data. In practice, it's training hundreds of smaller networks simultaneously and averaging the prediction. When comparing the results, the model with dropout shows a smaller gap between the training and validation accuracy compared to the model without it. Validation accuracy becomes more stable across epochs and generalizes better. The training accuracy grows more slowly since half of the neurons are dropped. The end result is model that performs more reliably on new data. Dropout is only active during the training. During interference, all neurons are used, and the outputs are scaled to account for the dropped neurons. So, for the summary, to summarize what we covered the assignment, in part A we explored 2D convolution kernels work and use them to detect lines or at 45 and 135 degree. We as well edges using three different kernels. In part B we trained CNN on CIFAR 10, analyzed its architecture and behavior, and improved it by adding an extra convolution block and a dropout layer. The key takeaway are convolution is foundation of feature extraction in CNNs. Deeper models can learn more complex features but are also more prone to overfitting. Regularization techniques like dropout can effectively reduce overfitting and improve generalization. Thank you for watching.